thermostat was on. I don't know if that does anything or not, but we'll see. I turned it down. Okay, we'll go ahead and get started. Can the people on Zoom hear me okay and see the quiz on the screen?
Yes.
Yes.
Thank you. So welcome back. Hope everyone had a nice spring break. I don't know about you, but it seems like it was about a year ago that we were in class, not a week. So what we'll do today is we'll go ahead and review the answers for the quiz that you took right before the break, and then we'll continue on with the acid-base equilibria chapter and go from there. So, all right. And as I go through the quiz, if you do have any questions or anything, please ask. And just to remind everyone that the quiz answers are posted on Canvas. So if you want to take a closer look at them later, you can do that as well. The first question, at equilibrium, the answer for that is at equilibrium, the rates of the forward and the reverse reactions are equal. So even though we have that equilibrium constant, things are happening. It's just they're happening at the same rates. So the concentrations stay the same. Number two, which of the following expressions is the correct equilibrium constant expression? For this reaction, the key here was noticing that CO2 was listed as a solid, H2O is a pure liquid. And so those two don't show up in the equilibrium expression because by definition, that means they're one. So the expression is hydrogen ion concentration times HCO3 minus concentration. Then number three, acetic acid reacts with ethanol to form ethyl acetate in water. And then there's a note here that in this reaction, water is a product rather than a pure liquid. So sometimes water is a product or a reactant in a reaction. Sometimes it's the pure liquid, the solvent. In this case, it actually was a product in the reaction. So that meant that it did show up in the equilibrium expression. Then you were given some information. You were given the equilibrium constant, and that value was 6.68. You had 15 liters of solution. You were given the molarity of it for acetic acid, 0.275, and methanol, 3.85. And then you wanted to find the equilibrium molar concentration of acetic acid. So the answer is 0.003, but how do we get that? Let's go down to where I worked out the problem, and we'll go through this. So the first thing I did is I wrote out my reaction. So acetic acid plus ethanol gives me the ethyl acetate and then water. And that equilibrium expression then is next what's expressed, the ethyl acetate concentration times the water concentration divided by acetic acid concentration times the ethanol concentration. So that's the products over reactants expression. Then I set up this little table that we talked about in class and did in some of the example problems and some of the homework problems. So I had the initial concentrations that I wrote out. That was the 0.7275 for acetic acid and 3.85 for ethanol. And then the ethyl acetate and water were started out at 0. Then there was some change that took place. And so based on my stoichiometry, I said that change was X, so it's minus X on the acetic acid, minus X on the ethanol, then plus X for water and ethyl acetate. And I know it's just X for each of those because it's all a 1-to-1 going to 1-to-1 in terms of the stoichiometry of the reaction. So then I wrote what it would be equilibrium. So equilibrium would be minus X for each of my reactants, and then X for each of the products. And I plug those values into the equilibrium expression. So I would have X times X in the numerator, 0.275 minus X times 3.85 minus X in the denominator. And that's equal to that 6.68 value that we were given in the problem. Well, this is where now the math fun begins. So you go ahead and start doing your algebra. And this is what we talked about in class. You just got to practice this stuff to get used to it and be able to kind of do it without really getting bogged down. So here, work through the algebra. You can kind of follow along on that. You get to the bottom and you get an equation, 5.68 x squared minus 27.6x plus 7.08. If the algebra part's confusing you, take a look at how I worked it out, try it on your own. I guarantee you this will come back again at some point, probably on the final exam. So the purpose of getting it into that form was we need to use the quadratic equation. And so up at the top here, I have the ax squared plus bx plus c equals c. Got that formula into that format. So then I could plug in things into the quadratic equation. That's the minus b plus or minus the square root b squared minus 4ac over 2a. If I plug those coefficients in, and the coefficients I'm talking about are for this equation, okay, so that was the thing we solved for before. I can plug those values in, then go ahead and solve. And remember, with quadratic equation, we have that plus or minus. So we do one solving with a plus, one solving with a minus. The solving with it plus is 4.57. The solving with it minus is 0.272. So then remember, we get those two answers, and then we have to make a decision on, usually one of them doesn't make much sense. And so we go back to our original table, and we saw that our starting concentrations, 0.275 for the acetic acid, 3.85 for the ethanol, tells me that when I look at the one with the positive sign, 4.57 molar, that's too big. Okay, it doesn't make sense in terms of what I started with. So that one's not a realistic number. So 0.272 molarity is what I'm going to use. I think some people kind of stopped at this point, but you weren't done yet, because what we wanted the acetic acid concentration. So remember, the acetic acid concentration, as we said, started out at 0.275, but at equilibrium, which is what we wanted, it's 0.275 minus x. So that value we just solved for, sorry, I keep scrolling back and forth here, but that value that we solved for here was the x value. So we needed to go take the 2.72 and subtract that from 0.275 to get 0.003 molar. By the same token, if you were looking for the ethanol concentration at equilibrium, you would do a similar thing where you take the initial minus this x value that we solved for to get that concentration. So the tricky thing about those problems is there's a lot of opportunities to make mistakes. And so if you got that one wrong, I would just suggest you go back and take a look at the worked out problem, but more importantly, make sure you can reproduce the math. Because as I've said multiple times now, there's a lot of pushing of buttons on your calculator, a lot of opportunities to mess something up. It's really easy to mess something up on those problems. Okay. The next one, number 4. Which of the following expressions is the correct equilibrium constant expression for the reaction below? So in this case, it's the SO3 in the numerator. That needed to be squared because of the 2 coefficient in front. And then SO2 times O2 in the denominator. The SO2 has a 2 in front of it, so that one is squared also. Number 5, acetic acid is a weak acid that dissociates into the acetate ion in a proton in aqueous solution. Then we have the reaction there. And then we're told at equilibrium at 25C, a 0.1 molar solution of acetic acid has the following concentrations. And then we're given equilibrium concentrations for the acetic acid, the acetate ion, and then the proton, hydrogen ion concentration. So we wanted to calculate the equilibrium constant for this. So what we would do is we would look at our reaction and then products over reactants. So acetate concentration times hydrogen ion concentration divided by acetic acid concentration. That would equal K, our equilibrium constant. So we would simply plug in those numbers because they're all already in molarity, so we're good there. So it'd be the 1.33 times 10 to the minus 3 times 1.33 times 10 to the minus 3 divided by 0.0990. And then we can solve for the K and get a value of 1.79 times 10 to the minus 5. Okay, and number 6. Number 6, we're told that H2 and Br2 react to form 2 moles of HBr. And then we're giving some number of moles of H2, moles of Br2 that are in the reaction vessel. And then we're told that at equilibrium, there's 0.546 moles of H2. And then we're asked to solve for equilibrium, how many moles of Br2 are there at equilibrium. So if we take a look at the H2, we're told there's 0.546 moles of H2 present at equilibrium. We know how much we started with, which is the 0.682. So if we simply subtract those two numbers, it tells us how many moles of H2 reacted, okay? And that value is 0.136. We know that the stoichiometry is 1 mole H2 reacts with 1 mole of Br2. So if there's 0.136 moles of H2 that reacted, then we know that there had to be 0.136 moles of Br2 reacted as well. So we simply then would go and see that we started with 0.440 moles of Br2. We subtract out the number of moles that we know reacted, and then we get 0.304 moles Br2. Okay, so number 7. For the endothermic reaction, calcium carbonate going to calcium oxide plus CO2, Le Chatelier's principle predicts that what will result in an increase in the number of moles of CO2. So of the choices we had, the one that will give you an increase because it's an endothermic is increasing the temperature. So remember, endothermic means you have to put energy into it to make it go. Temperature, heat, obviously, is energy. And so it's like adding more reactant to it. So you add more reactant, it shifts that equilibrium. Number 8, if the value of the equilibrium constant is much less than 1, then the equilibrium mixture contains mostly, and the answer for that is reactants. Remember, we have products over reactants. So if that denominator is really big, then it's going to be a smaller number. The denominator is the reactants. Okay, number 9. We're given a reaction of PCl5 going to PCl3 and Cl2, and we're told that the equilibrium constant for that reaction is 1.10, and we want to then express it in terms of on a concentration base. And so hopefully you remember that there was this relationship between KP and KC that told us that KP equals KC times gas constant times the temperature in Kelvin raised to the difference in moles between products and reactants. So change our temperature, which was 250 C to Kelvin to give us 523 Kelvin. We look at the number of moles difference. We had 2 moles formed, 1 mole that we started with in terms of gases. So 2 minus 1 is 1. So now we know our gas constant is 0.08206. We can plug in the R value. The T value we know now is 523. That power, the delta N number is 1. So we plug all that in. We're solving for Kc, and you get a value of 0.0256 or 2.56 times 10 to the minus 2. Okay, and then the last one, we're given an equilibrium constant, once again, for that same reaction that was above. And then we're given an initial pressure for the PCO5 of 0.123. And what we want to calculate is the PCO3 pressure at equilibrium. Okay, so just as we did on the earlier problem, we have our equation. We were actually given that in the previous in number 9. So we have our reaction equation. We then write our equilibrium expression. Once again, that's products over reactants. So we have PCO3 times Cl2 divided by PCO5. Set up our little table of reactants and products, and then initial change in equilibrium concentrations. So we had start with 0.123, 0 and 0 for the products. At equilibrium, some amount reacts. We're defining that as X because they're all 1, 1, 1 in terms of coefficients. So PCl5 is minus X, PCO3 and Cl2 are plus X. And so that tells us that at equilibrium, PCl5 will be 0.123 minus X, PCl3 and Cl2 will be X. We plug those into our equilibrium expression. So we have X times X divided by 0.123 minus X equals the constant we were given, which is 0.0121. Once again, then that starts doing our math. We can kind of go through and do the algebra, get to our equation set up so that we can plug it in, x squared plus 0.0121x, 1.49 times 10 to the minus 3. We set up our quadratic equation as we did before. Set up our quadratic equation as we did before. We get down here where we do our plus and minus solving. We have a choice of 0.0330 or minus 0.0451. Once again, in looking at that, the minus value doesn't really make any sense to have a negative concentration. And so we go ahead and then, because we want the concentration of PCl5, we need to go back here and see equilibrium at 0.123 minus X. If X is 0.0330, we do that subtraction and we get 0.090. So any questions about the quiz? Like I said, if you had any problems with these ones that use the quadratic equation, go back and take a look at them, work through the math to make sure you're comfortable with that and comfortable with using your calculator for it. Like I said, these will show up again. You know, we'll have a test in a week or two here and be a final exam, things like that. So hopefully you understand the process, and then it's just a matter of executing. All right. Let me pull up. Okay, so we had started talking about acid-base equilibria, and we had talked about how we define acids and bases before the break. So we're going to continue on with that discussion. So one thing we need to define is we need to define something called the ion product constant. And for water, that's designated as K sub W. And so really what this is the equilibrium expression for water. So if you think about it, water's H2O. If it's the pure liquid, has a value of 1, so it doesn't show up. But water does dissociate a little bit on its own. So most of the molecules are present as H2O. The vast majority are. But there are some that are present as H3O plus, and some that are present as OH minus, and those balance out. So when you write that equilibrium expression for water, it's H3O plus times OH minus in the numerator. The denominator would be H2O, but as I said, H2O is that pure liquid, so it's 1, so it doesn't show up in our expression. And so KW is something you'll see we use over and over, because KW is equal to 10 to the minus 14th. And you'll see in a bit here as we go through some of the other slides that we use that to be able to figure out what concentrations are of things, knowing that it's going to be overall 10 to the minus 14th. When we talk about aqueous solutions, we tend to talk about, are they acidic or basic or things like that. And so I think most people are familiar with pH, but we're going to talk a little bit about what pH is and where it comes from and what it means. So if a solution is neutral, that means that the hydrogen ion concentration and the hydroxide ion concentrations are equal, okay? Now, I just want to remind everyone, here when I wrote that expression, it was H3O plus and OH minus. Now we're saying H plus and OH minus. H3O plus and H plus are used interchangeably, okay? Technically, you should be saying H3O plus, but people rarely do that, to be honest with you. Usually you just write the hydrogen ion concentration. So if a solution has a hydrogen ion concentration that's greater than the hydroxide ion concentration, we say that solution is acidic. If a solution has the hydrogen ion concentration less than the hydroxide ion concentration, then we say that solution is basic. So in the examples that we have down below, we have hydrochloric acid, we have water, we have sodium hydroxide. Hydrochloric acid, that dissociates fully. You got a lot of hydrogen ions there. It's acidic solution. Water, in theory, is neutral as at 10 to the minus 14, pH 7. Water is, in theory, is neutral with the hydrogen ion and the hydroxide equal. In reality, it's rarely neutral. Like if you take your pH of your tap water or something like that, it's never going to be 7. I'll tell you that right now. Hydroxide ion, sodium hydroxide is a pretty common base. There, the hydrogen ion concentration is pretty low. and the hydroxide ion concentration is high. pH is the term people usually talk about when they're saying if something is acidic or basic. So we don't go around saying, oh, my solution is acidic because it's 1 × 10⁻² molar hydrogen ions. We don't typically say that kind of stuff. We usually say what the pH of something is. And pH is defined as minus the log of the hydrogen ion concentration. So for these, if we had a solution and we knew the hydrogen ion concentration, we'd plug that in here, we'd take the base 10 log of that, and then we would change the sign. That neutral solution where the pH, whether the hydrogen ion and hydroxide ion concentrations are the same, that will give you a pH of 7.00. If something has a pH below 7, we say it's acidic. If it's above pH of 7, we say it's basic. The other thing about this is when we see, like in these examples where it's 7.00, in terms of significant figures, it's just the numbers to the right of the decimal that indicate that. The one in front, the 7, that's giving you a feel for what the exponent was on the concentration, okay? So to take you back long ago, you didn't have calculators and you had to do all this stuff in log books. So you literally had these little books you carried around to look up what the logs of things were. And so this is how you remembered that the first digit here really had to do with the exponents. The next digits had to do with the number in front. So there's your old trivia for the day. On the right here, there's some examples of stuff that you come into contact all the time and gives you a feel for the pH. You see one of the most acidic things is stomach acid. You see that's 1 × 10⁻² concentration, hydrogen ion concentration. So that's a pH of 1. That's really acidic. That's why if you ever have like acid reflux or anything like that, it burns, it literally burns. And maybe you'll take a Tums or something to try and neutralize that acid. The stomach acid is pretty strong. A couple others here, cola and vinegar, you see is 10⁻³ vinegar. If you remember from last semester in Gen Chem lab, that's acetic acid. It's dilute acetic acid, actually. The cola one is funny because there's all this stuff people on the internet saying if you put a nail in Coca-Cola, it'll dissolve it. If you put a tooth into Coca-Cola, dissolve. That's all false. It will not do that. It'll turn it black, probably from the sugar, but it doesn't dissolve it. It's not that strong an acid. And besides, there's not a lot of acid. Anyway, I won't get off on that. On the base side, you see some real basic things. Bleach and ammonia are the two biggies that people probably encounter quite a bit. This is why you have to be a little careful with those cleaning products. You don't want to get something really basic and something real acidic. You can get certain combinations where you can get bad reactions. So the pH scale is what we typically think of when we think of something as acidic or basic. But the thing to remember is that little p in front of pH is just a function, okay? So in this case, it's minus the log of the hydrogen ion concentration. But in chemistry, we put the p in front of a lot of things. And so all that does is tell us we want to take minus the log of whatever is next. So we can have POH. So that'd be minus the log of the hydrogen ion concentration. We can have P times an equilibrium constant, in this case, the one for water. And if that's the case, what that's representing is pH plus POH. But remember, this was 1 × 10⁻14. So the pK for water is 14. And this is very useful, this pH plus POH equals 14. This is a useful relationship because if I know this, and then I tell you the pH is 4, what would the pOH be? Be 10, right. And so that's the beauty of this expression here, is that knowing that the pK for water is 14, if I know either pH or pOH, I can easily solve for the other without having to do a bunch of calculations. So pH is pretty important. It tells us if things are acid or basic. How do we measure them? Well, the most common way people measure pH is with a pH meter and an associated electrode. So in this example, the meter is the blue thing here, the little instrument thing in the back. The long cylindrical blue probe that's in the solution, that's a pH electrode. And the electrode senses differences in potential. And so those voltage changes result in telling you where the pH is going. And this is based on calibrating the electrode. Did you guys do this in this semester yet? Okay, so you had to calibrate that electrode, right? You had to put it in a solution that was a known pH and make sure it read the right thing. And then from there, you could go and read changes in pH. This is by far the most common way that in the lab, at least, people measure pH. There are a couple other things you can do as well. One is something called a chemical indicator. And what this is that the indicator changes colors as pH changes. The one that I know we did last semester with the titration was the one down here towards the bottom, phenolphthalein. So remember in that titration, it started out clear, and then as you titrated more, added more base, it started getting that slight pink color. And so what you see there is that phenolphthalein is colorless up to around about pH 8. And then from 8 to roughly 10, it gets pinker and pinker and pinker. And so there's a lot of different compounds that are known that have this color change, and you can see them on the bottom of the page here. They have different ones. Some of them most of them go from one color to another color. Phenolphthalein is the only one on this list, at least, that goes colorless to a color. But it's that same idea that as you go from one pH to another, you get some transition. Usually it's a protonation or deprotonation of the molecule, and it winds up getting a color change. And so those are kind of okay. Those give you a ballpark figure of where you're at. Certainly not as accurate and precise as the pH meter. So this semester, when you've done titrations, did you do it with the pH meter? Yeah. So you should have gotten better data with that because you really can track it. Whereas this depends on you watching it and not being impatient and things like that. Okay. The other thing I will mention before we leave how to measure pH, there is a third way, which is somewhat similar to this, but slightly different. And this is used sometimes for quick pH measurements. And so you can also, they sell these test strips. And the test strips, there's all kinds of these, and some are better than others, but there's all kinds of these test strips. You put a little bit of the solution on, and it'll turn a certain color. And then usually you have a chart that's associated with the test strips, and it'll tell you if the good ones have like maybe about 4 different colors on them, and the combination of what those colors look like tell you a little more exactly what your pH is. But it's kind of the same deal as these chemical indicators that we have here. It's the same idea, just a little more sophisticated. But that's a real easy way to get a quick, pretty good pH measurement if you're doing like a reaction or something like that. I think they sell those for like swimming pools and aquariums and things like that, those test strips and stuff. Okay, any questions on what we've gone through so far before I move on to a couple example problems? Okay. So let's take a look at a couple example problems from the homework. In 16.17, we're talking about Bronsted-Lowry acids and bases. And we want to identify the conjugate acid-base pairs in these reactions. Does anyone remember what you have to have happen for a Bronsted-Lowry acid? Yeah, it has to donate a proton, and then the base has to accept a proton. So that's what we're looking for here. So in this case, we have NH4 plus, the ammonium ion, going plus the cyanide ion, Cn minus, forming HCN plus ammonia. So in this case, we see that the NH4 plus, we look on the other side for something that looks similar to that. So in this case, it's the NH3. On the left-hand side, the NH4 plus had to lose a proton to become NH3. So it donated that proton somewhere. In this case, it was to the cyanide to form HCN. So that tells me that the NH4 plus is the acid and the NH3 is the base. So that's one pair. Then if that NH4 plus was an acid, Cn minus doesn't have a proton to donate. So I know that can't be the acid, but HCN does. So that HCN would be the acid to go with its conjugate base, which is Cn minus. The next one, CH3N plus water, going to CH3NH plus OH minus. Once again, we're looking on each side to see which of the molecules can either donate or accept a proton, and then going to the other side to see what its conjugate is. So in this case, we see the CH3, three of those on a nitrogen on the left-hand side of the equation. On the right-hand side, we see that it's picked up a proton there. So we see that the CH3N doesn't have a way to donate a proton, whereas the CH3NH plus does. So that tells me that's the acid in this pair. The CH3CN, CH33CN is the base. So then we look at the water and the hydroxide, but we should know right off that OH minus is a base, okay? So we know this is the base here. Water can either be an acid or a base. It can either donate a proton or pick up a proton, either way. In this case, because we've got the hydroxide over here, we know it must be acting as an acid there. So our conjugate acid base pair for those two are the acid is the water and the base is the hydroxide. Then the final one, we have HCOOH, and then we have HCOO minus. So we see that we have a proton that can be donated and wind up with the anion here on the right-hand side. So there's our conjugate acid base pair there. We see with the PO4 minus 3, the phosphate ion, there's no proton that can be donated there, so that's got to be a base. On the right-hand side, we have the HPO4 minus 2. That has the ability to donate a proton, so that's the acid on that form. So you should be able to look at an equation like this and figure out which ones are donating protons, which ones are picking up protons, and then match them up as the conjugate acid base pairs. And the thing to remember is, because we call them conjugate acid base pairs, for instance, the PO4 part is going to go with the other one that has a PO4. The HCOO is going to go with the other one that has a HCOO. The HCOO isn't going to go with the PO4 or something like that because they're not conjugates in that fashion. Any questions on this? Okay. Let's take a look at another problem, number 1629. So in 1629, we're asked for each of these solutions to calculate the hydrogen ion concentration and then say, is the solution acidic, basic, or neutral? Okay, so the first thing we want to do is remember what was our equilibrium constant for water. And remember, the equilibrium constant for water is hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the minus 14. So if we're given either the hydrogen ion or hydronium ion concentration, or we're given the hydroxide ion concentration, we can plug those into this relationship and then we can solve for whatever we're missing. So in this first one, we're told the hydroxide ion concentration is 0.0045 molar. So these do need to be in molar. The molarity is the units that we have to have those concentrations in. But this one is already in, so we simply can plug that value into our equilibrium constant for water. And then we can solve for the hydronium ion concentration. And we get 2.2 times 10 to the minus 11 molar. Well, we want to know if it's acidic or basic. For me personally, it's a lot easier to think of something's acidic or basic if I think in terms of pH. So if I do minus the log of this hydronium ion concentration, that gives me a pH value, and that calculates out to 10.7. 10.7 pH, that's higher than 7, and we said if pH is higher than 7, then it's a basic solution. So I know in this case, this is a basic solution. Okay, in part B, in this case, we're given a hydroxide concentration of 8.8 times 10 to the minus 9 molar. Once again, we take advantage of that water equilibrium constant being 1 times 10 to the minus 14th and plug in our hydroxide concentration and solve for the hydronium ion. We go ahead and take the minus the log of that value, and we get a pH of 5.9. That pH is less than 7. If it's less than 7, then it is acidic. Now, the third problem is we're told that the hydroxide ion concentration is 100 times the hydrogen ion concentration. So we're still going to use that expression, that 1 times 10 to the minus 14 equals hydroxide ion concentration times hydrogen ion concentration. We're still going to use that relationship. But instead of having a number in here for the hydroxide ion concentration, we're going to put in 100 times the H plus. So we have 100 times H plus times H plus. If we do that math, we get 100 H plus squared, okay? And so then we can go ahead and solve that for H plus and get a value of 1 times 10 to the minus 8. If I go ahead and take minus the log of that 1 times 10 to the minus 8, then I see my pH is 8. pH is 8, higher than 7, so it's a basic solution. So this one's a little bit tricky just because instead of them giving us a number to plug in, we had to do a little bit of algebra. Okay, any questions about any of that before I move to the next problem? Okay, so in 1635, you're given this table. Hydrogen ion concentration, hydroxide ion concentration, pH, pOH, and then asking you if it's acidic or basic. So I'm not going to go through working out the math. You guys can do that on your own when you're working on the homework. But I do want to talk about just kind of the thought process behind filling in something like this. So the things to remember, what's pH? pH is minus the log of the hydrogen ion concentration. pOH, minus the log of the hydroxide ion concentration. pH plus pOH equals 14. H plus times OH minus is 1 times 10 to the minus 14. Remembering those relationships are the key to doing something like this table. So no matter what information I'm given, if I'm given, for instance, a hydrogen ion concentration and I want to fill in the rest of those, well, I can get pH real quickly by doing minus the log of the hydrogen ion concentration. Then I can get pOH real quickly by just doing whatever that pH was, filling that in, solving for the pOH, knowing that the total adds up to 14. If I have hydrogen ion concentration, I want to get hydroxide ion concentration. I can use this hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the minus 14. So these relationships, pH equals minus the log of hydrogen ion concentration, pOH equals minus the log of hydroxide ion concentration, pH plus pOH equals 14, hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the minus 14. Those 4 relationships, you can work with those in different combinations to fill in this table. The acidic basic, there you just need to remember pH above 7 is basic, pH below 7 is acidic. So I would suggest spending some time kind of going through that table and making sure you can calculate things out. Okay. So when we talk about acids and bases, remember we talked about strong acids and strong bases. We talked about weak ones as well. And really when we're talking about focusing on acids now, really what we're talking about when we talk about a strong acid is how many of the protons that are on the molecule of all those molecules dissociate and then show up as that H plus or that H3O plus. So when we put our pH meter in, we get a low pH value. So the most common strong acids are listed here: HCl, HBr, HI, nitric, sulfuric, chloric, perchloric. And what that means is for those acids, this dissociation, where HA represents just a generic strong acid, goes into water, donates that proton to the water, and we're left with H3O plus or H plus, however you prefer to think of it, and then the anion to the acid. In a strong acid, we're saying that pretty much happens completely. There might be a tiny bit that doesn't dissociate, but really, for all practical purposes, it donates fully. And what that means is this hydrogen ion concentration, this hydronium ion concentration, is the same concentration as the acid. Okay, because it's dissociated completely. we have similar thinking about strong bases. So the soluble hydroxides are almost all strong bases. So things like sodium hydroxide, potassium hydroxide, things like that. Those are strong bases. So just as we said, the acids dissociate to where you wind up with hydrogen ions and then whatever the anion, associated anion is. It's a similar thought with strong bases. So if this MOH is serving as a generic strong base, you put that into water and you get whatever that M is as a positive ion, and then you have hydroxide. Depending upon what that M is, if it's has a charge of +2, then you would get 2 hydroxides formed. You have M+2 and 2 OH minus. And there are a few things, like here calcium hydroxide is an example, barium hydroxide is an example. The more common ones, though, are the sodium and potassium and lithium and things like that. But the point on this is, for strong bases, just as with strong acids, this dissociation is usually pretty much complete. You put sodium hydroxide into water, that concentration of hydroxide is going to be similar, essentially the same as whatever the sodium hydroxide concentration was because of that complete dissociation. So for strong acids, strong bases, complete dissociation, that's the thing to remember. When we talk about weak acids and weak bases, that's where that equilibrium constant really comes into play. Because in those cases, it doesn't all go, for instance, for weak acids, it doesn't all go to protons. So in this kind of generic equation here, where HA on the left is a weak acid, we'll have some that dissociates into H3O plus and A minus, but there's still going to be some in the form of HA. And so depending upon how much that gets donated, that tells us how strong the acid is. And so when we write that equilibrium expression, and this is the same expression that we've been writing all along, right? It's products over reactants. But in the terms of acids, we call it the acid dissociation constant, Ka. So in chemistry, the term pKa is used all the time when people talk about compounds. Because pKa, what it does, it gives us a feel for how much of this acid is dissociated, okay? And that has implications in terms of reactivity and a whole bunch of other things. So you think of it as, that's telling us how likely that acid is to donate the proton, right? And what you'll see here in a moment, when we were talking about those strong acids, and let's just go back for a second and look at those, let's see. One thing you notice about these strong acids, or maybe you don't notice this, but there's something these strong acids have in common. Anybody have a guess on what it is? None of them have carbon, okay? So when we're talking about these, they typically call mineral acid type acids, those are strong acids fully dissociate. When we start talking about weak acids, as you'll see, for the most part, what we're talking about are compounds that now have carbon in them. It's not 100%, but for the most part, that's what we're talking about. And those are the compounds that we're really more interested in, to be honest with you, in terms of reactivity and stuff like that. And so that's why this pKa term is really important, because this is how we determine how dissociated things are, and then how that impacts maybe reactivity and stuff like that. So the larger the Ka value, the stronger the acid. That makes sense. If this number is big, then that means our numerator is bigger than our denominator. What's in the numerator? It's H3O plus, right? that means that's probably a big number. And so that tells us higher that number, the stronger the acid. Now, I will say that people don't typically talk in terms of Ka, just like with pH, we like pH. That's nice and simple to say pH of 4 or 8 or something like that. It's the same with Ka. Usually you don't talk in terms of acid dissociation constant. You talk in terms of pKa. So that would be minus the log of this Ka value. So I mentioned a little bit about some of the acids. So when I think of weak acids, so down at the bottom here, benzoic acid is a good example. This C double bond O with a single bonded O and then a hydrogen on that single bonded O. That functionality is a carboxylic acid. So those are real popular acids in the chemistry world. Everybody likes carboxylic acids. Acetic is another one. This is our friend that was in vinegar. The same functionality there. You'll see that carboxylic acid on the end. Phenol down at the bottom, that's a pretty weak acid, and you can tell by its 1 × 10 to the minus 10th Ka value. So these are weak acids. Technically they're acids, but really it's those carboxyl groups that people are usually more interested in. So this is just a repeat of what I was saying before. Strong acids, they dissociate into the ions. Weak acids, it's that partial dissociation into the ions. And that's where that acid dissociation constant comes into play for those weak acids, to give us a feel for how much it dissociates. Okay, so how do we use an acid dissociation constant to calculate pH? Well, let's go through an example. So if we have a 0.10 molar of formic acid, and here's formic, HCOOH. So that COOH, that's that carboxyl group I was mentioning. So that you'd have a double bond going off the C and then a single bond to the O and then the H. Excuse me. We're told that the pH of a 0.1 molar solution, so we made up the solution, we weighed stuff out, it's 0.1 molar. We measured the pH and we get a value of 2.38. So then we want to know, well, what's the formic acid? We want to calculate the Ka for the formic acid at this temperature. Well, we can write that equilibrium expression. It's the reaction would be the formic acid, the HCOOH plus water going to H3O plus, and then the formate anion. So the water, once again, is a pure liquid, so it's a 1. So our equilibrium expression, hydrogen ion concentration times formate ion concentration divided by formic acid. So to calculate Ka, we need the equilibrium concentrations. So what do you think we're going to do next? Hopefully in your mind, you're saying we're going to set up that table, which we'll do in a moment. But before that, let's just go ahead and convert what the hydrogen ion concentration is in molarity. Remember, we were given it to us in terms of pH. So if we're told the pH is 2.38, to convert that into a concentration, we raise 10 to the minus 2.38 power. Okay, so that's that anti-log that we're doing. So we raise that to 10 to the minus 2.38, because remember, we were told here pH is 2.38, and pH is equal to minus the log of the hydrogen ion concentration. So to reverse that, 10 to the minus 2.38, we get 4.2 times 10 to the minus 3. We know that that's the hydrogen ion concentration because we were told that. But we know from the stoichiometry of the chemical equation that hydrogen ion concentration and formate ion concentration are going to be the same. So that tells us that each of these are going to be 4.2 times 10 to the minus 3. So here's our table that we like to set up. We have our initial row, we have our change row, and then we have an equilibrium. So at the top here, we have listed the 3 concentrations in molarity that we're interested in. We were told that we started with 0.1 molar of the formic acid, no hydrogen ion, no formate ion. We know from our pH measurement what that, in our little calculation we just did, we know what the hydrogen ion concentration and the formate ion concentrations are. That's the 4.2 times 10 to the minus 3 molar. And we know that if this is how much dissociated, this is how much formed, then that had to be the amount that was lost of the formic acid based on the reaction stoichiometry. It's all 1 mole, 1 mole, 1 mole. So we go ahead and say at equilibrium, it's 0.1 minus this 4.2 times 10 to the minus 3. For the hydronium ion, the hydrogen ion, it's that 4.2 times 10 to the minus 3 that we were told from our pH measurement, and same for the formate ion. Okay, so we can go ahead and do the subtraction here to find out what it is at equilibrium for the formic acid. And we see that 0.1 minus 4.2 times 10 to the minus 3 equals 0.0958. Well, if we are sticking to our significant figure conventions, okay, because we started with 2 significant figures for this concentration. If we make this 0.0958 2 significant figures, it's still 0.10, right? And this is what you're going to see is one of the things that happens quite a bit in this weak acid equilibrium stuff. Is remember before we had to trot out the quadratic equation and go through that 2 pages of calculations to get to that? Here's an example of where we see the amount that this dissociated relative to what we started with is pretty small. And if we stick to our significant figure conventions, the number actually didn't change, did it? So keep that in the back of your mind as we go on to some other examples. So here, just to finish this one out, we go ahead and solve this. And we get our value for Ka. Another calculation that you can do is something called percent ionization. And percent ionization is simply the equilibrium hydrogen ion concentration divided by the initial concentration of the acid. Since it's a percent, then we multiply it by 100. So in this example, if we're saying at equilibrium, our hydrogen ion concentration is 4.2 times 10 to the minus 3 molar. Our initial is 0.10 molar. We do that ratio, then times 100. Percent ionization is 4.2%. So when we go back here, okay, what this difference here between the 0.1 and the 0.958 represented was really 4.2%. That's the amount of ionization. So does that matter? Well, sometimes it does, sometimes it doesn't. More often than not, this is not significant. And so that's one reason why a lot of times, instead of going through that whole quadratic equation to solve these kind of problems with acids, we don't. We just make an assumption that relative to what we started with, it doesn't really matter because the amount of ionization is pretty small. And that's what we're talking about when we're talking about weak acids. We're talking about a smaller amount of ionization. Those strong acids, HCl, things like that, that would be 100% here. And so you have much more of a dissociation than you have with the weak acids. Okay, so let's talk about calculating pH using Ka. And if you recall, when we were talking about some of these equilibrium calculations, there was a slide that I said, you really should learn this slide. This is an important slide. Make sure you're comfortable with the thought process on this slide. I'm saying the same thing about this slide here. And it's very similar to that other slide. Hopefully you're getting a feel for this, but we're talking about these different equilibrium expressions. And we're talking about in terms of acids and bases and just different things. And so there are some subtle differences there, but fundamentally it's all the same thing, right? And so the approach is going to be very similar. We want to write the chemical equation for the ionization equilibrium, okay? Then we want to write that equilibrium constant expression. Then we want to set up that table, initial, change, equilibrium, and then use that X variable to plug in what we don't know and the changes in that. And then the final thing on this one that's a little bit different is what we talked about just a moment ago, is sometimes you can make assumptions to make the math a little bit easier. And they're reasonable assumptions in these cases, because you're usually doing this on a weak acid or a weak base. We'll talk about the base version of this in a little bit, but it's the same idea. Okay, so let's go through an example problem. So we're going to look at 0.3 molar acetic acid solution. And so the first thing we do is we said we're going to write out our chemical equation. So we have acetic acid plus water gives us that hydronium ion plus the acetate ion. We write our equilibrium expression, H plus times acetate concentration divided by acetic acid concentration. So we know what our products are, we know what our reactants are. We're going to build our table like we've been doing. So we have acetic acid concentration, H plus, and acetate, all those expressed in molarity, moles per liter. And then we write in what the initial concentrations are. 0.3 molar, we were told, was our initial solution. Initially, we don't have any dissociation, but then we wait a few moments and we have our dissociation. That change in concentration we're going to find is X. So some amount of the acetic acid dissociates. And because of the stoichiometry being ones across the board in front of those molecules, and our equation tells us one acyl form of the H3O plus, one acyl form of the acetate ion. And then finally, we can express this as equilibrium, 0.3 minus X, X, and X. Like I said, very similar, should look pretty much the same as what we've been doing all along. It's that same thought process. So we fill in those concentrations. We have X times X in the numerator, 0.30 minus X in the denominator. Here's where, with these weak acids, we can often make an assumption. So if we assume that X is going to be a pretty small number relative to 0.3, okay? And if you think back on that example we did on the formate, I think it was what, like 3-4% or something. That's a pretty small amount, especially when we only have two significant figures in our concentration. So what we do is we go ahead and we're going to say this X compared to the 0.30 value is really, really small. So we're going to ignore it. Makes the math a heck of a lot easier, okay? So instead of having to trot out our friend, the quadratic equation, and if you really love the quadratic equation and are attached to it, feel free to drag it out and leave that X in there and solve it for all that. That's fine. But if you're like me and probably most people, that it's like, yikes, this is a lot of work, and I usually make a mistake when I'm pressing the calculator buttons and I got to go redo it. And this is an opportunity for these types of problems to neglect that. And so now you have a much more simpler x squared over 0.30 equals our equilibrium constant. Then we can solve for x, 2.3 times 10 to the minus 3. Remember, x was equal to our hydrogen ion concentration. So if we do minus the log of that value, that gives us our pH value, which is 2.64. So weak acid, we're setting up the problem similar. We've been setting up all these equilibrium problems. The big difference, though, is since it's a weak acid, we're saying that we're going to neglect this bit of dissociation that occurred, that because relative to what we started with, it's a small number. And because of that, that takes us away from using the quadratic equation to solve for x and puts it back to more straightforward algebra. Okay, any questions about that? All right. Just saying it for another time, once again, strong acids, that equilibrium hydrogen ion concentration is going to be the same as whatever that starting concentration was of the acid. For weak acid, the equilibrium hydrogen ion concentration is going to be a lot less than that initial acid concentration. And that's because the weak acid is telling us it doesn't fully dissociate. And we get a feel for how much it dissociates by looking at that Ka value, that dissociation constant value. So sometimes acids have more than one acidic proton on them. So sulfuric acid is an example, phosphoric acid, that's an example. There's a bunch of organic acids that have more than one. The protons get removed in a certain order, okay? And so each of the protons that gets removed has its own dissociation constant. So it has its own pKa value. And that first proton that comes off is the easiest one. And then there's usually a gap between the next ones. And that's where you'll see for compounds that have protons, multiple protons that can be donated, there'll be multiple acid dissociation values for that. And that's reflective of how hard it is to get those next protons to donate. In general, as a rule of thumb, if that difference between the Ka values is 10 to the third or greater, then really the only one that really matters usually is the first one, okay? So there's some things that have protons that can be donated, but they don't just happen easily. It's not like they donate all that first proton and they move on to the next one and keep going. And that's because that difference in Ka values are bigger enough that you have to do something to it to get the next ones to go. And here's some examples of this. So let's see, so like citric acid, for instance, you see 10 to the minus 4, 10 to the minus 5, 10 to the minus 7. Citric is one that will donate, okay, because those pKa's, or rather the K, I always want to say pKa, but the Ka's are very similar. Oxalic's kind of on the edge. Phosphoric, though, no. You put phosphoric acid in solution, it'll fully deprotonate that first proton with this Ka of 10 to the minus 3. To get it to start kicking off the second or third protons, you have to add base to adjust that pH to get it to push off, okay? So even though you have multiple protons that can be donated. Some are easier to have it do it than others. Okay. I'm going to stop here because we're about to start on the bases and I don't want to get going on that midway and stop midway through. So Thursday, we'll continue with this discussion. And then we'll just go from there. Any questions before we end? Okay, thanks.